So, welcome everyone to the Recurrent ETDS seminar. Today, to our pleasure, we have Barak Weiss, who will be telling us about the illumination problem and dynamics. Over to you, Barak.
Okay, thanks, Nishant. All right, so just interrupt me at any time. This is a talk that I gave to undergraduates without much experience in dynamics, and I'm going to, and I added some more details for people who are more dynamically inclined, but most of it is just about an application which I think is very attractive of ergodic theory to a nice elementary but difficult problem in geometry. So. Yeah, so please stop me at any time if I'm not if you're not understanding me. So let me remind you about the law of the billiard flow. So you have a polygon. So I'll draw a polygon, and I'm making one edge straight and nice, and just imagine that this is some kind of polygon with lots and lots and lots and lots of uh, lots and lots and lots of edges like this. And we're given a point, and we're given a direction. And the definition of the dynamics is you move in a straight line, and when you hit the wall, you bounce off, and the law is that the angle of incidence equals the angle of reflection. And then you keep going, and you bounce off the next wall, and you bounce off the next wall. And if you hit a vertex, the dynamics is undefined. And so just as a warm-up exercise, so oops, the set of x theta, where x is a p is this polygon, and theta is a unit circle, and the billiard flow starting at x in direction theta is defined for all time. This set is large in the sense of measure and in the sense of category. So what do I mean by this? So this is where the dynamics takes place in a in this product space. I'm sorry, I'm looking for the pointer. Yeah, the dynamics takes place in this product space where the x's lives inside the billiard table and the thetas live in the circle. And I've just defined for you how they behave, but of course there's the issue of hitting vertices, and I'm claiming that hitting vertices is not what shouldn't deter you from studying the dynamics here, because the dynamical system is going to be well defined in the sense that there are going to be trajectories that don't hit vertices. And in fact, in this product space, if you think about it, measure theoretically using the Lebesgue measure on X and the circle measure on the thetas, all but measure zero, a set of points will never hit one of these vertices. And similarly, you can think about this in the language of Baire category and see that it's a big set, it's a residual set. Okay, so this is the billiard flow, and we're interested in studying how points move in the billiard flow, and people study it from various angles. And here's the question that was asked by someone named Straus, Ernst Straus, in the 50s. He asked, is there a polygon containing 2 points which don't illuminate each other? This is why it's called the illumination problem, where illuminate means There's no billiard trajectory between these points. And okay, the illumination language or the illumination terminology comes from the idea that you can think about this as a kind of a hall of mirrors, and you can think of this as a laser beam that you're shining in a hall of mirrors, and you want to know whether from every point you can reach every other point. So of course, if the table, going back to this picture, if the table, the billiard table is some convex shape, say like some kind of quadrilateral like this, and you take any 2 points and you just can just connect them with one straight line, and there's nothing to worry about. But if you start with a complicated shape and you have these 2 points A and B here, who's to guarantee that you can get from A to B by a billiard path? So this was an open problem. Is the question clear to everybody? So this was an open problem for some years, and then it was settled in the negative. So examples were found by Tokarsky. So Tokarsky, 95, said that this does happen. And his proof, I'll show you the examples now. His proof, I made pictures. So this is the first example. This is a so-called famous Tokarsky example. So these 2 points A and B here don't see each other. So let's just think about what happens on this shape. If you're trying to go from A to B in a straight line, you run into this vertex. If you're trying to go from A to B with one bounce off the wall, you might want to go like that, but it doesn't happen. You hit exactly this vertex. If you're trying to do it with, say, 3 bounces, 1, 2, 3, 4, you hit this vertex, and so on. So Tokarsky proved that there's no way to get from between these 2 points. The proof is an elementary proof using geometry of triangles, and it's important to notice here that this shape is tiled by triangles. The triangles are isosceles right triangles, and the 2 points, when you do the tiling, the 2 points are vertices of one of the triangles in this tiling. Tokarsky had more examples. Here's another example. Again, the 2 points are this point and this point. And again, this is a shape tiled. It's not as easy to see, but this is a shape tiled by a long, thin triangle like this one, and lots and lots and lots of triangles in this shape. Okay, and again, the 2 points that don't see each other have this feature that they come from vertices of the triangle of one of these triangles in the tiling, and these are the only examples. No, there are more examples of this type, but all of them use this an elementary fact about triangles. Here's the example with the least number of sides. This is in this example, these 2 points don't see each other. This is an example of Voletsky. When he was part of his master's thesis under my supervision, and again, tiled by these isosceles right triangles, and the points are corners. So all the examples known have this feature, but we don't know. We don't have a. Okay, so here, so let me
Barak,
sort of up.
I
Yeah.
have a question. Can't
Sure.
any polygon be tiled by isosceles right triangles? Well, they can all be tiled by triangles. That's
The triangles need to be identical isosceles right triangles.
Oh, okay.
And also another feature which I didn't mention is whenever you have a triangle in your tiling, the adjacent triangle should be obtained
Face to face.
exactly by reflection along one of the sides. So it's not just tiling; it's tiling identical triangles by reflections. Okay, so it's very, very kind of a restrictive construction. Okay, so here's some updated questions now that we know that these examples do exist. So updated. Questions. Question 1. is there a polygon P and X and P such that the set Y and P such that X does not illuminate Y contain an open set. Question two, same set, could it be infinite? And in other words, is there an example? In these examples that I just showed you, there are just 2 points that don't see each other. You could work a little harder with these triangles and get finitely many points that don't see each other, but that's all that's known. So the answer to this is a theorem that I want to tell you a little bit about. So theorem of Lelièvre, Montet, and myself. And I think the accent is like this. And this is about 10 years ago. Don't remember the date. So this, let me just copy this. So there exists, so for every polygon P with rational sides in every X and P, the number of Y's such that X doesn't eliminate Y is finite. So that answers questions 1 and 2 negatively. It's always a finite number. And then there's a follow-up theorem of Voletsky, whom I mentioned earlier, who was my master's student, and this is approximately 6 years ago, roughly. And it says a stronger result. So for every P with rational sides, the number of pairs of points which miss each other is the number of pairs don't eliminate each other is finite. So this is a stronger result than the preceding one. And I'm going to tell you just briefly how these 2 theorems are proved. I'm not going to go into all the details, but I'll give you the general strategy. And one thing to note is that everything I've said in these 2 results is about is with this condition about having. Sorry, I said rational sides, and it's not what I meant. I meant rational angles. Sorry. Let me. So what is a rational angle? A rational angle should be rational if it's measured in degrees, or in other words, I want if I'm measuring using radians, I'd like all angles to be rational multiples of pi, or in other words, to occupy a rational proportion of the circumference of a circle. So this is, all the angles should be like this. If at least one of the angles is irrational, we don't know anything. We don't know these restrictions at all. But on the other hand, we don't have any examples of such polygons with irrational sides where we have a pair of points that don't eliminate each other. So the problem is completely open for irrational polygons, and rational polygons are you can analyze them using dynamics in a better way, and that's sort of what you're going to see in this talk. But of course, it's very natural and teasing to try to remove this hypothesis about the rationality, but it's going to require a new idea. Okay, any questions about the geometric theorems? So these are the theorems.
So one question I have is, once you're given this polygon, do you think that there's an algorithm? Maybe the algorithm takes a very long time, which gives an answer to this question. Because it's all rational angles, you can feed all of this to a computer.
Certainly not now, certainly not at the moment with our current understanding, but I'm hopeful that in the next few years we will have a theorem that says something along the lines, I don't know exactly how to formulate it, but something along the lines of the only examples of polygons which contain points which don't illuminate each other are polygons which are tiled by triangles, or maybe tiled by some small collection of other polygons, perhaps. And the points that don't illuminate each other should be vertices of these polygons, or maybe slightly less restrictive condition. Once we have that, and I think somehow the technology at hand might make such a theorem possible. We don't have it yet. And of course, once we have that theorem, then the problem will become decidable for rational polygons, because that's easy to check. But
if I have any 2 points given, and if I just want to check whether I can illuminate, say, point Y using point X, even then I have infinitely many angles to check, right? So
there's infinitely many angles. There's also infinitely many
time.
combinatorial. Okay, the billiard flow is not continuous. So what
Right.
happens is somehow, just imagine that this is part of a polygon and I'm illuminating. So all the trajectories that hit this wall sort of bounce off one way. Then there's this special trajectory here where the billiard flow is not defined, and everything on the other side does something completely different. And so this is a point of discontinuity for the dynamics. And as you make the trajectories longer and longer, you're going to see more and more of these points that hit vertices, and the lack of continuity will be kind of worse and worse. And that makes any kind of compactness argument impossible somehow. And so, yeah, so it is sort of an infinite search to try and figure out where all the trajectories are going. You can't, or here's another way to say this. Suppose I shine my light beam in all directions and look at the points that I get by traveling a fixed distance. So this is a circle for a small amount of time, but then it hits the discontinuity point, and it stops becoming a circle, and it's some kind of I don't know exactly how to draw it. It's some kind of object like that with a torn circle. But then if you keep pushing this further, what you're going to see for large T is just a huge collection of small segments or small arcs, which are very, very far away from each other and have nothing to do with each other. They've forgotten all about the others. And so it's a hard problem.
So even for 2 points and rational angles, right now you don't see an algorithm.
No. No, like I said, this problem, it was open for a while.
Sure.
And you're going to see that the techniques in the proof that we have are very, very indirect, very indirect. You're not going to see it exactly. You're going to get a taste of it in a moment. Okay, so now I'm going to, any other questions about the theorems?
Yeah, so I have a short question. So in the previous theorem, where you fix an x and then you count the number of y's. So
Yes.
we have examples. I'm just curious. We have examples for a given x where there exists two y's or something like that. The cardinality is greater
2
than 1.
y's for 1x. Nobody's written it up, but one could do it using these triangles.
Okay.
For example, I think if you let me go back to the pictures. I think if you take this shape and you sort of continue it like this, you see what I mean? Like periodically add this triangle and add this thing that looks like a circle to the right.
Mm-hmm.
All of these points in the corner.
Okay.
I'm not going to
Makes sense, yeah.
I haven't checked details, but I'm almost certain that's going to happen.
Okay, makes sense. Yeah.
Okay, so I'm going to switch to dynamics, and I'm going to introduce a little bit of the kinds of dynamics. So if we're going to forget about illumination for a few minutes. So what is dynamics, and what are the sort of central problems in dynamics from the point of view of this lecture? You have a space, X is a space, and maybe it's a measure space, maybe it's a topological space. For the purpose of this lecture, okay, it's kind of weird. You should think about it topologically, but when we were just talking about the billiard dynamics itself, we realized that the topology is a little bit funny because of these points we have to remove. Nevertheless, for the next few minutes, just ignore that. And let's just think of X as being a nice topological space, for example, a complete metric space. So let's say for now, complete metric space, like some manifold or something like that. G is a topological group. E.g., we could take a discrete group like the integers, or we could take, we're going to take SL2R, the group of 2 by 2 real matrices of determinant 1 is going to play a role in this lecture. And we have an action, so G, this is notation for an action. G acts on X, so what this means is that we have a map that takes the product, Cartesian product, G cross X to X, and it's a continuous map with respect to the topologies. So we have a topology on G, we have a topology on X, and so we have a topology on this product, and with respect to this topology, we want this map to be continuous, and it should be a group action. So let's denote this in the standard way for group actions, and then the axioms of group actions are that if you apply an element G1 to G1 to G2X, you get the same as this, and of course here, this is an element of X, and so we're applying the group action twice. First, this is an application of the group action, and this is an application of the group action. Here, this is an element of G, so we multiply in G, and then we apply. So we're applying the group action once. So this is, anyway, this is the definition of a group action. And when you have a group action, you have a point. So given x0 and x, the orbit of x0 is all the places you can arrive at by applying elements of G. And the type of questions that we want to understand is sort of like question, classify closures of orbits. Now, I'm going to give you two examples. You're going to see that this is a very ambitious goal in dynamics. It's not common that you can classify all the closures of all the orbits, but I'll just give you two examples, one in which this is possible and one in which this is not possible. So example one is an irrational rotation. So here X is the quotient of R by Z. It's the one-dimensional circle, which is identified with the unit circle by the map X mod Z, which is 2 pi X. And this is X, and G is the integers, and n times x, the action law is t, I'm going to write it this way, t at alpha x, where t alpha of x is x plus alpha for some alpha in an irrational. So let's just, you've probably all seen this before, so I'll do this quickly. This is the addition rule in this group. This quotient group is also a group. This torus is a group. So we're just adding alpha, which is an irrational number. And when you want to do it n times, you just repeat n times. And the reason it's called a circle rotation is if we think about this parameterization by the circle, and we have a point x here, and we move the point to the point obtained by rotating the circle by an angle of alpha. So this is T alpha, this is T squared alpha, etc. And now, since alpha is irrational, there are no periodic orbits in this dynamical system. And using that, it's not hard to show. So let me use that as an exercise if you've never seen this before. It's a fun exercise if you want to, it's a nice exercise to give to undergraduates, actually. So all orbits are dense in this dynamical system. So the orbit closures are always one and the same thing. They're their entire space. Okay, so that's example one. Example two, X will be, this is the shift map. X will be the set of bi-infinite sequences indexed by integers. So this is an element of X. And T will be the shift map. If this is an element, after applying the shift map, you have the same elements in your infinite sequence, but their indexing is shifted by one. So in other words, if X has this form, let's say this is the zeroth. I'll just give one example of a sequence. Suppose it starts with 3 occurrences of 0, 1, and then repeats infinitely often with ones in the let's say this is our sequence, and the decimal point is just telling us how they're indexed by integers. So this is like the 0th entry is the one to the right of this decimal point. So Tx is the same sequence except the decimal point is moved by 1. So now this is the 0th entry, or another way to think about this of what I've done in this picture for you, since it was easier for me when writing, is I've moved the decimal point to the right, but maybe it's more common to think about this as if you're moving the entire symbols, the infinite sequence of symbols, one step to the left. And we have to put a topology on this object, and the topology is given by the metric. The distance from X to Y is 1 over K, where K is the maximal J such that X I equals Y I for I less than J. So another way to think about this is two sequences are close to each other if they agree on a big prefix, and the bigger the prefix, the closer they are, where prefix here is measured in two directions, in the forward and backward direction. So this is the symbolic space, and now I want to convince you that there are plenty of different orbit closures for this in this example. So for example, if X equals the 0 sequence, an infinite sequence of zeros in both directions, then this is a fixed point for the action. Shifting it just maps it to itself. So the orbit is 1 point, so the orbit closure is 1 point. You could have complicated, say, this is the period that I want, and now I can repeat. So if I haven't made a mistake, I chose a repeating block of length 7. And so what this means is that t to the 7th of x equals x. And so this is an orbit of length 7. And so similarly, I can construct orbits, periodic orbits of any length that I'd like. And I can also make my orbits accumulate on everything that I like. It's easy to construct a dense orbit. So to construct a dense orbit, append or concatenate. I hope I'm not boring you. This is like standard material, but concatenate all finite words in one word. So there are orbits which are dense, there are orbits which are finite, there are orbits which are not dense and not finite. You can easily, for example, if I construct a letter that has, an infinite word that uses all letters and it does not allow any occurrence of 2 consecutive ones, but allows everything else, then I'm going to get an orbit which is neither dense nor periodic, and so on. And there's a theorem, for example, a folklore theorem that I don't know who to attribute this to, that says that for any theta between 0 and 1, there exists x in x such that t to the orbit of x, such that the closure of the orbit of x has Hausdorff dimension so you can basically get any Hausdorff dimension that you like it for some orbit closure. So in this dynamical system, it's very far from possible to classify all the orbit closures. There's just too many possibilities. So this is the dichotomy that I'm trying to emphasize, that for some dynamical systems, it is possible to classify orbit closures, and for some it's not. And it's actually, in dynamics, it's much more common that it's impossible to classify the orbit closures, but there are some in which you can. The bigger the group, of course, the fewer the orbits. Somehow, philosophically, the orbits should be larger, and that should make this goal more attainable. And indeed, that's what you're going to see in a moment. So now I'd like to introduce a very particular dynamical system, which is, so this was generalities, and I'd like to introduce a dynamical system, which is the moduli space of translation surfaces. So I'm going to give you a very, very short introduction to what translation surfaces are. So definition, and this is not the best definition, but it's sort of the more convenient one for a brief introduction. A translation surface is an equivalence class of finite collections of polygons with edges partitioned into pairs of equal length and parallel. And where equivalence is generated by cutting, translating, and gluing polygons. I will explain what I mean by a picture. So this is an example I'm giving you an example of a translation surface, and this is one example. And this is another example, but it turns out that these two examples are equivalent, so they're actually the same example. So let's do this slowly. So what you're seeing here is one polygon. And if you look at its edges, they fall into pairs of edges, which are parallel and of equal length. So for example, this edge and this edge are parallel and of equal length. This edge and this edge are parallel and of equal length. This edge and this edge are this edge and this edge and this edge and this edge. So all the edges of this polygon are sort of paired up with a friend of equal length. And the same for this one here. This is paired with this. This is paired with this. Actually, this shape is a decagon, and the opposite sides of the decagon are parallel and of equal length. Now, why are these two polygons the same? You can get from one to the other by chopping up this polygon into little triangular pieces, which are indicated in the diagram. And so these additional lines, you cut along these additional lines, and you translate each piece by a different amount. So this piece is translated here, this piece is translated here, etc. And you form you form the shape on the right. And what's important in these attaching maps is that they have to respect the parallel edges. So in other words, here we have a triangle, it's mapped over here. This edge is paired up with this edge. And so they need to be adjacent. If they're not edges anymore on the resulting surface, they need to be adjacent. So this triangle is indeed mapped to this triangle. And so this edge and this edge are both mapped to this edge. So this is an example. I didn't write that down in my definition, but that's a requirement. Okay, so a more maybe intrinsic way to think about these objects is that they define surfaces for us. Topologically, these are surfaces, and I think of these identified pairs of points as just a quotient, topological quotient. So any point on this edge is identified with the corresponding quotient on the other edge by translation. And these are surfaces, and the surfaces carry some additional structure that's inherited from the plane, like angles and directions and lengths and areas make sense on the surface. Okay, on these objects, there are finitely many points which are the vertices of the polygon, which come from the vertices of the polygons, which get identified in interesting ways. So look at these black points. This black point is identified with this black point. Earlier I said that the edges are paired up, but you should think of those paired edges as being glued to each other. So this point and this point are the same because this edge and this edge have been glued to each other. But also this point is the same as this point because this edge has been glued to this edge. And similarly, this point, this edge is glued to this edge. So this point here is glued to this point here. And so if you work it out, the black point, all the points marked in black in this picture are actually the same, and all the points marked in this empty circle are actually the same. And if you think, you can measure the angle around these points. So what I'm going to do is I'm going to rotate around this point, and you'll see what happens as I do that. I go around, and because of the gluing, I continue here, and I keep going around. And because of this gluing, I'm back over here, and I keep going around, and keep going around, and keep going around, until finally I'm back here. So when I do that, the point sees, if you will, an angle which is bigger than 2 pi, and these are called singular points. And these objects are parameterized by numbers. This 1, 1 notation means that there are 2 special points, and each has excess angle 2 pi. So the 1 means the amount of excess angle in multiples of 2 pi. Okay, that was your brief introduction to what a translation surface is. Now there's a space of all possible translation surfaces of the same type. So let me write that down. Curly H, A1, K, denote collection of all translation surfaces with k-singular points. These points that I mentioned, these special points that I mentioned earlier, are called singular points, where the ith point has cone angle. These are called cone angles. Cone angle 2 pi ai. This one. So what this is saying is if ai were 0, then the angle would be 2 pi, which is what you see in a regular point. And if ai is 1, you're getting an extra 2 pi. The bigger ai, the more excess angle you get. So ai is measuring the excess of the angle at point I. So you stick all of these points together, and you also add the requirement that the area of these surfaces is 1. Area can be measured just by adding the areas of the polygons, and that's a well-defined area. And it turns out that this is a manifold. So how does this become a manifold? Let me go back to the picture. What's a neighborhood? First, I'd like to put a topology on these collections of these pictures. And what's a neighborhood of, say, of this shape? A neighborhood is obtained by perturbing slightly the location of these vertices in the plane. So you can think of, as a first approximation, you can think about how do you put all polygons with the same number of sides as part of a topological space? Well, you just identify the edges with points, the vertices with points in Euclidean space. So if your polygon has k sides, then this is an element of r to the power 2k. It records all the possible locations of all the vertices. Now, we're identifying things which differ by translation, so that cuts down the dimensions. And we're also requiring that some edges are parallel, and that cuts down the dimensions. But still, the set of all polygons which satisfies certain conditions inherits a manifold structure just from the ambient Euclidean space. Now, there's a lot to check here, which I'm not doing, like particularly when you change from one representative of the equivalence relation to another, what happens? This is sort of the main issue. Okay, but that can be done. It's not a trivial thing, but it can be done, and we have a well-defined space. Okay, now SL2R, the group of SL2R, what's called G, acts on the plane by linear transformations thus on polygons, and thus on this moduli. This is called the moduli space of translation surfaces. Okay, so again, let's show a picture again. So so here's one polygon, and here's another. They represent two translation surfaces. Just ignore this line in the center of the picture. It's not relevant for us today. How do you get from the first picture? They're not identical. How do you get from one to the other? You apply a linear transformation. It's recorded here. So if you apply this particular linear transformation, the horizontal lengths are unaffected, but the vertical sides move, the points move horizontally, depending on whether they're up above or below this axis. The points over here don't move. These points move a little bit. And you get from this picture to this picture. And so the SL2R action is making this translation surface into this one. And we can ask about the dynamics of this action, and we can ask about the orbit closures. And just as to get your first glimpse, if you've never seen this before, let's just think about what happens when we apply. Let's just start with a simple shape. Well, it doesn't have to be simple. Any shape, actually. I'll just draw some random translation surface made of, I don't know, two polygons. And I'm not telling you how sides are glued to each other or anything. Now let's take a sequence in this group SL and R, It's not interesting to think what they're doing when they converge to something. So let's just think that they're not converging to anything. They're getting bigger and bigger. So the GNs look like 2x2 matrix with determinant 1, but big entries. So for example, it's not that easy to come up with determinant 1 matrices, but let's just say 1,000,001 and 2,000 and 5,000. That's an example of a matrix of determinant 1. So what is this matrix? I hope I got my arithmetic correct. No, I need a 10 million, sorry. Maybe it's correct now. So what is this matrix doing? Well, it's got a big eigenvalue and a small eigenvalue. In fact, there's a very big eigenvalue and a very small eigenvalue because the product is 1. And so it's got a huge it's got a vector which is stretched by a huge amount, and then a vector which is squeezed by a huge amount. So let's just assume, I don't know the directions of these eigenvectors, but let's just assume that they're in a kind of a diagonal direction. So what this map is doing to these two polygons is it's just stretching them immensely, making them very long and thin in some direction. Is this clear? The linear action is preserving area. So it's transforming this polygon into some polygon which is stretched enormously in one direction, but squeezed enormously in another. So it looks like some kind of random long shape. And it doesn't seem like this is converging to anything reasonable. So you might think, well, the action is doing nothing interesting in terms of dynamics, but that's very false. The action on the space of polygons is not interesting, but the action on translation surfaces is not the action on the space of polygons because of this equivalence relation. So what you should imagine is that this new polygon, this stretched long polygon, can be cut up into 1,000,001 little pieces and rearranged by equivalence to some other shape. And that's the dynamics that we care about. Okay, I hope this was sort of clear. Okay. And there's the very famous by now, Mirzakhani, Mohammadi paper. So the paper eventually got published. So this has a long history, which I'm not going to review here, but eventually got published in 2013. And it's based on a previous paper by Mirzakhani that actually got published later in 2018. And these two papers together classify orbit closures for this action. Okay, so you may have seen when I was flipping upwards and backwards to see the pictures. I had pictures of Mirzakhani and Eskin. I'm not going to, when I gave the talk to students, I tell them a little bit about Eskin and Mirzakhani because they'd never heard of these people. I'm hoping that you have. These are very important dynamicists. Unfortunately, Maryam Mirzakhani is no longer with us. She passed away quite young. This is Maryam Mirzakhani. This is Alex Eskin. Maryam received the Fields Medal basically based on the work that I've just described. Eskin received the Breakthrough Prize based on the work that I've just described. Eskin donated part of the winnings of this to a memorial fund for Mirzakhani. So now there's a Mirzakhani Prize using Eskin's winning as a seed money. And this is a picture that I like. This is a picture of Maya Mirzakhani by some random artist who got inspired by hearing him. If you've ever seen Maya Mirzakhani give a lecture, she was very, very inspiring, but very confusing also. And she was very, very active and energetic. And it was hard to figure out exactly what she was saying. And her blackboard sort of did look like this. She just filled them up with all sorts of things that came up to her head. And so this is very representative of her style of speaking. And here we see Tokarsky, and here we see the illumination problem. So she was aware that her work led to these results about the illumination. She was very, very aware that how one got from her results with Eskin and Mohammadi to these illumination results. So I'm going to spend just a few minutes, very few minutes, explaining that and sort of connect it to parts of my talk. Before I do that, any questions about what translation surfaces are and what the results? I'm not telling you the classification result. I'm just telling you there is a classification, but what you should take away from this is orbits are dense unless there's a pretty good reason for why they should not be dense. And if they're not dense, they're dense in some submanifold, which one can describe rather explicitly. So the orbit closures are very structured. That's what you should take away from this discussion. Any questions before I go on to the how you apply this very roughly? Okay, so I'm just going to spend 5 minutes on this. I hope that's fine. So there's something called the unfolding procedure. So when you start, let me explain it my way and then show a picture. So when you start with a polygon and you're playing billiards in the polygon, this is where rational makes an appearance. So given a rational, one can unfold it as follows. Glue, let's call the rational polygon P. Glue, define a group. Let delta be the group generated by reflections on the sides of P. Delta is finite because P has rational angles. So this is where rationality comes in. And you glue delta 1 of P to delta 2 of P if delta 1 of P has an edge E fixed by the map delta 2, delta 1. Oops. And it turns out that what this is, so I'll just show one example. So maybe this is P, and this is one of the edges of P. And in this group delta, there's a reflection that doesn't touch E, but it reflects in E. So roughly speaking, this is delta of P. So we got a new polygon from the old polygon, and they have this edge E, which is stable by this map, and we just identify these two polygons to each other. And so we get a finite, you could think of these polygons, I've drawn them as if they were adjacent. You can sort of think about them as everything is well defined up to translations. So just move them for visual purposes, just think about them as being separated some distance, and you identify those two edges to each other in the way that we've described. So this collection of polygons is finite and all edges are paired up. And so we got a translation surface from this construction. And what's the relation to billiards? I'll write it down and then I'll show you a slide. So billiards in P is analyzed via straight line flow, resulting translation surface. So let me explain that with a slide. Okay, here what we do is we start with this polygon, this triangle. And we're interested in billiards in this triangle. It turns out that the group generated by the reflections in the side has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16 elements. And so when you rearrange when you reflect this triangle by all possible triangles, you get this shape. As a translation surface, it's actually equivalent to this regular octagon. For example, here, this triangle is right here. If I reflect it in this side, I get this triangle. If I reflect it in this side, I get this triangle. And finally, if I reflect it in this side, I get this triangle, okay? And so they're all sitting here. Now, the billiard map is supposed to take a point and make it jump around inside this triangle. But because of the law that says angle of reflection equals the angle of incidence, if I think about what it's doing in the reflected side, this side, instead of the original side, after reflection, the reflected path will just join the original path in a straight line. And so the trajectory of the billiard flow becomes a straight line flow in this object. And this is the straight line flow. It's easy to explain. You just pass through the picture using the identifications. Okay? So analyzing the straight line flow is the same as analyzing the billiard flow. Okay, what does this all have to do with the SL2R action? Now I'm getting to the punchline. The punchline is very, very short, but I'll just tell you the punchline. So what does this all have to do with the SL2R action on the space of translation surfaces? And what does this have to do with illumination? So SL2R maps straight, acting on the plane, maps straight lines to straight lines, obviously. Imagine that this translation surface was very, very complicated, actually, and I didn't really know whether there was a straight line from this point to this point. Of course, this happens to be a convex polygon, so I do know that answer to that. But let's just pretend that I don't know. And then I managed to find one, and that one that I found was extremely complicated, sort of wrapped through this picture 300 million times, and finally connected this point to this point. Now let's just apply an element of SL2R to the entire picture. The element of SL2R takes this octagon to some other shape, takes this translation surface to some other translation surface, takes this point to some other point, and this point to some other point, but most importantly, it takes the straight line between them to some other straight line between the new points. So SL2R action is preserving the property of being illuminable or non-illuminable. And that's the crucial business. And if you think about it a little harder, you actually see that the space of surfaces, the space of translation surfaces admitting pairs which do not see each other by the straight line flow is closed if you make all the relevant notions in the right topology. So we're exactly in a setting of classifying closed invariant sets for this dynamical system, which is exactly what Mirzakhani theorem is about. One more piece of information. Suppose the orbit happened to be dense. Suppose the orbit of, I don't know how to map, I don't know whether there's a straight line from this point to this point, but suppose the orbit happened to be dense under SL2R. Well, if it's dense, then this shape, which looks very simple in the picture that I'm showing you, but just imagine it's extremely complicated. After applying the SL2R action, I can make it simpler. Maybe it becomes exactly this shape. And the 2 points that I want to connect, I just see them inside a convex polygon. Then obviously I can connect them in an easy line. So that means that on my original surface, if the orbit was dense, the illumination, there are no examples. The illumination problem is solved. There are no points which don't see each other on this. Yeah, so that's the point, basically. Most orbits are dense, and the ones which are not dense have explicit descriptions. The explicit descriptions are explicit enough for us to be able to say certain things about them. For example, those two theorems that I mentioned. And I'm hopeful that with more progress in the field of understanding the dynamics on the moduli space of translation surfaces, we will be able to even say more about these examples where we have points which don't illuminate each other. This is still very much an active area of research. Okay, let me stop here and hear your questions.
Thanks a lot, Barak. Let's thank him for a wonderful talk. Questions from the audience? So, Barak, a trivial question to start off
Yep.
with. This SL2R action doesn't keep billiard flow as billiard flow, right? Because
Does not keep what? I didn't hear you.
doesn't keep billiard flow as billiard flow, right? Because
No, there is no billiard flow on, if you don't do the unfolding,
then it doesn't make sense, right?
yeah, it doesn't map billiard trajectories to billiard trajectories. It destroys the angles.
Somehow,
But
once
if
you
you
do
pass to the translation surfaces, you can use it.
So, there's sort of a, yeah, maybe I should wait for others.
If people want to ask questions,
So,
send
uh,
email. Yes.
Yeah, so as far as I understand, this theory of translation surfaces doesn't work at all for irrational polygons, right?
Exactly.
So,
There is a theory there. You can talk about infinite. You can unfold an irrational polygon, and what you get is an object which people call it a translation surface of infinite type. So instead of having finitely many polygons with glued edges, you have infinitely many polygons. And there's a little bit of understanding of what's happening in that theory, but it's much less developed and much harder. And probably that's not the correct approach to understanding the billiard.
the feasibility problem at all, I mean, like, doesn't connect to this infinite type translation surface.
I mean, it would connect, but it seems like a very, okay, I wouldn't go, that's not what I think we should do if we want to. I don't know. I don't know how to do. Let's just put it this
Okay.
way. I don't know how to do it.
And is there I mean, this is a really dumb question. I mean, like, is there a real rephrasing of the visibility problem in terms of interval exchange? I mean,
No, it's not a
or does it
dumb.
even make sense?
It's not a dumb question, but the answer is no. The reason is the interval there's a very tight connection between these translation surfaces and interval exchanges, but for the connection to work, you have to fix a direction. So if you go to this picture here, and you want to look at the map, say in the vertical direction, oops, anyway, my
I
iPad
lost the.
yeah, my iPad lost power, but it's not important. So
Hmm.
if you take a translation surface, fix a direction, move in that direction, and wait until you return to an interval inside the translation surface, you get an interval exchange transformation. And this is a very good way to study that particular interval exchange transformation. However, for the billiard flow and for the illumination problems, you're interested in all possible flows in all possible directions. So you're actually getting like a one parameter family indexed by direction of interval exchanges. And this is certainly interesting and certainly can be analyzed in this using these ideas, but it's not, it's not very there's not a snappy way to say the connection. For example, I'll just give you a very famous example. There's a famous theorem of Kirchhoff, Mazur, and Smiley from the 1980s, and it says that in the billiard, for rational billiards, in almost every direction, in the sense of Lebesgue measure, the flow of the billiard in that direction is uniquely ergodic. That's a well-known theorem of Kirchhoff, Mazur, and Smiley. That's proved using translation surfaces. So this almost every direction corresponds to varying inside the circle of directions and thinking about what's happening in this moduli space of translation surfaces. So it is a useful thing to do, but it's not very easy to do.
Thanks.
Let me stop the share because this device is not working. Yeah.
Barak, do you have a few minutes to talk?
Yeah.
So I had a couple of questions. Uh, so I have been on and off trying to think about billiards in three dimensions for polyhedrons.
Yeah.
So just something as well known and simplistic as say Mazur's theorem for in a rational polygon you have then like if you give me any point and direction you'll find some point which is close by and a direction close by which is there any like so uh, I know from experience now that this is very very hard.
Yeah.
Like what about the illumination problem in three dimensions? Is this
Nothing, I'm not aware of any results. The technique that I told you about is very, very particular to rational polygon in the plane with rational angles. Very, very little else is known.
In fact, I have been trying to just come up with a elementary proof which does not use homogeneous dynamics for Mazur's theorem, and have been unable to do that.
Well, I'm not surprised because just think about, Mazur is telling you not only that there are periodic orbits, but there are plenty and plenty of periodic
Yeah,
orbits.
that's right.
Now, if you pass to irrational polygons,
Uh-huh.
that's a very, very famous open problem. It's not known whether there's even one periodic orbit on every triangle, for example. That's like probably maybe should have said it, but that's probably the most famous question in billiards is there a periodic trajectory for any billiard
Right.
in the play? So it's not surprising to me that you failed because if you had managed to do it in 3 dimensions, probably you would have managed to do it for irrational triangles.
Uh-huh.
Nobody's able to do that.
So another question I had coming back to the plane. So I'm trying to think like a discrete mathematician as I am.
Mhm.
And so the kind of surfaces you described were tiled by triangles, and in fact, very nicely by triangles. You took right-angled isosceles triangles, deflected them along the sides. You formed your surface, not surface. You formed your polygon, and then you want to study billiards on that. So let's keep it to this because again, one of my motivations in all of this is I can plug this into a computer. I can actually describe this completely to a computer. Now, if I just take two vertices that are obtained in this fashion, and I ask whether vertex one illuminates the other one, this is in some sense trying to find a path using these triangles in this graph, right? I can construct a graph using these triangles,
Yeah.
and there seems to be two inputs. One is the graph, and the other is some kind of very subtle Diophantine inequality. I don't know if I can put it that way, which takes care that the angles are well controlled. Now, what I'm getting at is, has anyone tried like the Diophantine problems are famously undecidable. Has anyone tried to approach it this way? Do you know?
I'm not completely sure. There are many, many people performing computer experiments
Mhm.
in this topic in general. I mean, this is like one of the most computer intensive fields that I know of in mathematics. Just the community.
Mhm.
There's a whole group of people sort of trying to do numerical experiments on these objects, and they come up with all sorts of interesting
Mhm.
phenomena. I don't know much more than that. But there's something called the Rosy induction map, which is
Mhm.
an analog of the continued fraction algorithm
Right.
for interval exchanges.
Mhm.
And it's more combinatorially more complicated, but it's sort of philosophically, it's very much the flavor of Diophantine approximation. And it's been programmed and run on lots of examples, quite a bit of effort. So that's all I can tell you. I mean, there's plenty of people involved.
Mhm.
You might ask them to tell you about it. I don't know that much about it, but I mean,
Sure.
there's plenty of people who are working on it.
Like, for instance, who would be able to?
Probably the Lelièvre, whom I mentioned, he was my co-author on this paper. He does a lot of computations. There's a guy called Delacroix, Vincent
Right,
Delacroix.
Vincent. Yeah. He.
Delacroix is very active in this field.
Mhm,
Pat Hooper,
mhm,
um,
mhm,
and yeah, they do a lot of computations and they see a lot of things. But passing from that to understanding, it's not enough for the computer to see something. It's also enough. You want to prove it and you want to understand why it worked.
Right. That's a very hard question.
And that's another layer of understanding. Like I don't know how satisfactory it is that I'm using this. Maybe I didn't say this in my lecture, but I mean, like this asking Mirzakhani result uses lots and lots and lots of tools from various different fields in mathematics, like probability theory and random walks and heavy analysis and all sorts of things go into that proof. And I'm using it to solve this very elementary geometrical problem. You might say that that's not very pleasing, but just imagine that I was giving you a proof, and the proof was a reduction to things that a computer could check, and then you ran the computer for 5 months, and the computer said, yes, what you wanted to, what you asked me is true. And there's your computer assisted proof. Now, are you more happy now? I don't know.
No. I think so.
Or maybe people don't care about proof so much. That's also maybe mathematicians are too obsessed about proofs.
So there are two kind of questions, right? One is for a specific example, trying to find out if you know that now you can build polygons where you cannot illuminate points. Now, can you explicitly find out what these points are? That's one kind of a question. And the other kind of question is the more abstract question where you ask whether the illuminated sets, the non-illuminated sets form an open set, and where, of course, the mathematical, yeah, uh, very different flavors of questions.
Yeah.
And
I think basically with these computers, they tell you the answer, and then you have to sort of have a lot of experience to decide whether you believe what they're telling you, because they're never going to give you an approach for a proof. They're just telling you what they see, but you could have made a programming error there, or there could be a floating error. There's all sorts of issues that are delicate. So you have to be a very good programmer to know that you're actually, if you don't have a mathematical reason to suspect that the computer output is correct, you know that from probability theory, right? There's a lot of people in probability do a lot of simulations, and they give a lot of talks based on simulations. And I think one should be suspicious sometimes, because if you make programming errors, it's easy to show things which have nothing to do with the facts.
Absolutely. Yes. Other questions? Okay. So thanks a lot, Barak. This was
Okay, guys.
a real
Nice
pleasure
meeting you all.
Right. Let me